Hey everybody, we are back and we're working on lesson 5, parent functions. So in this lesson, we're going to be talking about a library of functions that are the foundation for our course. We've been using a little bit so far, but today we're going to start talking about all sorts of parent functions that include domain, range, roots, y-intercepts. Sorry, I'm looking for my little pointer. Increasing and decreasing behavior, symmetry, even and odd, bound, something that's boundless, local extrema, horizontal and vertical asymptotes, and behavior and continuity, which are all things that we've explored before, but now we're going to look at them with every parent function. Remember that an even function is symmetric to the y-axis. So remember that test for even or odd functions, you plug in negative x. Things that are even are symmetrical about this y-axis. So we can see that it will spin this way and it'll be the same. Things that are odd are symmetrical to the origin. So we can see that it will spin around this origin and at about 180 degrees, it will come back to itself. And then things that are not a function are symmetric, can be symmetric to the x-axis. All right, so let's talk about this. So a constant function looks like this: f of x equals c. So we've got negative infinity to infinity is its domain. The range is just that value of c. The limit as x approaches negative infinity of f of x is c, and the limit on the other side as it approaches positive infinity is also c. The intercepts, we know that it has a y-intercept at 0, c. Other things that we know about it is that it's an even function, meaning it's symmetrical about the y-axis. It's continuous, and it's constant. Okay, and what it can look like, it can be any value. So I'm just going to call this value c. So in that case, it's somewhere between 3 and 4, but we can call any value c, and it's going to be a horizontal. This next one, we call it the identity function. It's where y equals x or f of x equals x. The domain, again, is all real numbers, and the range also is all real numbers. And as x approaches negative infinity to the left, the function approaches negative infinity down. And as the limit approaches x going to infinity to the right, the function also approaches infinity up. Intercepts that we see are at 0, 0, which is an x and a y intercept. It's an odd function. It's continuous. And it's unbounded. We also know that it increases on the interval from negative infinity to infinity. So for the entire function, it's increasing, and it looks like this. It starts at 0, 0, and it has a slope of 1. So for every value of x, it's the same value of y, and it looks like this. All right, let's talk about the reciprocal function. A reciprocal function looks like f of x equals 1 over x. Its domain, now remember, anytime you've got a denominator here, that means there's going to be a restriction on the domain. We can't have 0 in the denominator, so the domain's going to go from negative infinity to 0, and then start again from 0 to infinity. And the range will have the same, so negative infinity to 0, and then we'll start again from 0 to infinity. The limit as x approaches negative infinity is 0, and the limit as x approaches positive infinity is also 0. It has no intercept, so it doesn't cross the x or the y-axis. We do know that it's an odd function. It is discontinuous, meaning it has a discontinuity, and it has it's unbounded, but it also has a vertical asymptote at x equals 0, and that y equals 0 is a horizontal asymptote. And it looks something like this. It goes through the point 1, 1, and it goes through the point negative 1, 1 as well. Okay, let's look at the next one. The quadratic function, we've worked with this one a lot. We know quadratics are all reals. So the domain is all real, and the range stays above the value of 0. So it starts at 0, and it goes to infinity. The graph as it goes to the left, the limit as x approaches negative infinity is positive infinity. The limit as it goes to the right to positive infinity is also positive infinity. Its x and y intercepts are at 0. It's an even function. It's continuous. It's bounded below. And it's concave up. It's increasing from 0 to infinity, and it's decreasing from negative infinity to 0. And our graph, as you know, starts at 0, 0, and it looks something like this. All right, let's talk about our cubic function. Cubic function looks like this, where you've got x to the third. There's no restriction on the domain, so we know negative infinity to infinity, also the same for the range. The limit as x approaches to the left to negative infinity is also negative infinity. The right, as the limit x approaches infinity of f of x is positive infinity. We know the intercepts for x and y are at 0, 0. It's an odd function. It's continuous and unbounded. It increases everywhere. So it's increasing from negative infinity to positive infinity. It's concave down from negative infinity to 0, but concave up from 0 to infinity. And it looks like this. It starts at 0, 0, and it goes concave up and to the right here, and then here it goes concave down and to the left. Let's look at this next one. So square root function, we know the domain here, there's this red flag of this root. We know that x can equal 0 or a positive number, so the domain goes from 0 to infinity and includes the 0. Same thing for the range. It starts at 0 and goes up to infinity. The limit as x approaches 0 is 0, and the limit as x approaches infinity is infinity. Okay, we know there's an intercept at 0, 0. It's continuous. It increases from the interval of 0 to infinity. It's concave down. And it has no symmetries. And the way it looks, it starts at 0, 0, goes up, and it kind of starts to look like that. All right, next one. We've got the absolute value function. The domain, again, there's no restriction on it, so we say negative infinity to infinity. The range is from 0 to infinity. The limit as x approaches negative infinity goes to up to positive infinity, and the limit as it approaches to the right to positive infinity is also going upwards to infinity. It has an intercept at 0, 0. The function is even. It's continuous. It's bounded below. It's decreasing from negative infinity to a 0 and increasing from 0 to infinity. It looks like this, going from 0, 0, and it has a slope up of 1 to the right, and it has a slope of negative 1 to the left. Okay, let's look at our next one. This one, we've got our cube root function. So similar to the square root function, but this one is cube root, which means we can have negatives. So our domain and range are all real values. The limit of the function as it goes to the left, where x is approaching negative infinity, is going down to negative infinity, and x as approaches positive infinity to the right, it goes up to infinity as well. It has the intercepts of 0, 0. The function is odd, and this is continuous, unbounded. It's concave up from negative infinity to 0, but then it's also concave down from 0 to infinity, and it increases for all real numbers. So it's always increasing, and it looks like this. and it goes flat. Okay, that bottom doesn't look very good. Let's try again. There we go. All right, let's look at our exponential function. Our exponential function has no restriction on the x. Remember, that means it's in the exponent. So we know domain is negative infinity to infinity. But the range does have to stay positive. So from 0 to infinity. The limit as x approaches to the left is 0. And the limit as x approaches infinity to the right is positive infinity. And the intercept is at 0, 1. It's continuous and bounded below. There's no symmetry. And it's concave up. It has a horizontal asymptote at y equals 0. And it's the inverse of the natural log of x, where y equals the natural log of x. So it looks like this. So it goes through the point 0, 1. It hits the point at 1, e, which e is 2.7 approximately. And there's a horizontal asymptote here along the x-axis, so it looks something like this. Okay, let's look at the natural log or logarithmic function of x. So the domain can only be positive, so from 0 to infinity, but the range can go both positive and negative values. So the limit on the left side from x approaching 0 is negative infinity, and the limit on the right side as x approaches positive infinity is infinity. Our intercept is at 1, 0. It's continuous, unbounded, no symmetry, concave up, or excuse me, concave down. It's vertical. It has a vertical asymptote where x equals 0. And it's the inverse function of y equals e to the x. So it looks the opposite of the one that we just did, where it goes to the point 1, 0. And at 2, it will be the ln of 2. It'll look like this. It looks like that. All right, now we have this greatest integer function, which we've learned before. It's not quite the ceiling function, but this is what we call a rounding down function. So remember that our domain can be any real number, and our range is only the integers, which are like -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5, like that. The limit as x approaches negative infinity on the left is negative infinity. The limit as x approaches infinity to the right is infinity. The ideas that we have here, we have actually infinite intercepts, and you'll see why the step that goes along the x-axis is an infinite number of intercepts. We have a constant values of n, n plus 1. Where it's a constant function, it's discontinuous, and it's neither even or odd. It's unbounded, and it increases only on integer values. Okay, so this is a rounding function. So everything rounds down to the nearest x. So for example, if x is 0, it's going to round to 0. If x is 0.9, it's also going to round to 0. So we have an open hole on 1. So it looks like this. So it looks like this is an open hole. It looks like a step function. All right, next one. This one is also actually called a step function. It's called the signum function. and it's where we have the absolute value of x over x, and the piecewise function is it fills in a value where x is 0. So we say the domain is from all real numbers, but the range is only these three values, -1, 0, and 1. The limit on the left side as x approaches -1 is -1, and the limit on the right side as x approaches 1 is 1. It has intercepts at 0, 0. It's bounded. It's discontinuous. And it's constant. And it looks like this. So it has a value of 0, 0. At x equals 0, it jumps up at an open value here, and it goes 1 all the way to the right, and it goes open circle here, and it always is -1 to the left. And then we've got our sine function again, all reals for the domain. Range can only go from 1 to -1 to 1. The period is 2 pi. It's bounded, continuous, and periodic, which means it cycles back. Okay, there's 5 key points. Okay, we have an integer, a maximum, and this is kind of the pattern it follows. There's another integer, there's a minimum, and then there's an integer, and that happens at 0, 0. At pi over 2, 1 is the maximum. At pi, 0 is the integer again. 3 pi over 2, -1 is the minimum value. And then we've got another intercept, not integer, sorry, all of these are intercepts at 2 pi over 0. It has roots, meaning solutions or x-intercepts at every value of x equals pi times k. So I can multiply pi by any number, and I'm going to get a root there. As long as k is the set of, so we use this kind of like E, that we say includes the set of all real integers, z. Okay, we have an absolute maximum of 1, but it repeats, and we have an absolute minimum of x equals -1. And this is what our graph looks like. It goes at 0, 0. At pi over 2, it's a maximum of 1. At pi, it's an intercept again. At 3 pi over 2, it's a -1. And at 2 pi, it's an intercept again. And we don't do zigzaggies. We want to make sure that these look nice and curvy. Okay, now we've got our cosine function again, intervals from real numbers. Our range also goes from -1 to 1. The period again is 2 pi, very similar to sine. It's bounded, continuous, and periodic, meaning it repeats. Again, it has the same, it has 5 key points, but this time it's going to go in the cycle of a maximum, an intercept, a minimum, an intercept, and then another maximum, where we have those at 0, 1, pi over 2, 0, pi, -1 is your minimum, another intercept at 3 pi over 2, 0, and a maximum at 2 pi, 1. It also has solutions or roots at x equals pi over 2 plus pi times k, and it has an absolute max at +1 and an absolute minimum of -1. So for this one, because it's cosine, it's the peak is at 1, our intercept is at pi over 2, minimum's at pi, intercept again at 3 pi over 2, and a maximum again at 2 pi. And you want to connect these so they're nice and round. And then you can work this backwards to the left hand side. Almost done. We've got tangent, which is the domain of this at x cannot equal pi over 2 or any version of this pi over 2 plus pi from it. Okay, the range is from -infinity to infinity. The period is pi. We are discontinuous, unbounded, and it's an odd function. It has asymptotes where x is every pi over 2. and they're pi apart, and it has roots at x equals 0 plus or minus every pi, as long as k is the set of integers. Okay, so it looks like this. So every pi over 2 has a vertical asymptote, and we go pi away. So if I add pi, that's going to be 3 pi over 2, and so on. So we see our asymptotes here. In the middle of these at 0, 0, and then in the center of every vertical asymptote, we see your integers, or your intercepts, and they go up 1 and to the right, down 1 and to the left. Okay, let's look at cotangent. Cotangent is very similar. X cannot equal pi times k. The range is from negative infinity to infinity. The period is pi. It's discontinuous, unbounded, neither even or odd, and it has asymptotes at every pi value, and they're n apart. So we have asymptotes at every pi, so 1 pi, 2 pi, 0 pi, and negative pi. And in the middle of those, exactly in the middle, we have our intercepts. And in this time, instead of going up and to the right, this go up and to the left, down and to the right. All right, we got cosecant is the domain of x equals, or is not equal to pi times k. The range goes from negative infinity to 1, negative 1, and then it starts again from 1 to infinity. The period is 2 pi. It's odd, discontinuous. And I'm going to have you guys sketch these together with me the next time we see each other, because they're a little bit confusing. So I'm going to sketch these together in class. I'll see you next time.